So hi everyone, my name is Camilla, and thanks Marco for the introduction. So as I was just saying, I had zero luck with live demos this year, so unfortunately this will be rather heavily PowerPoint based, but I hope you enjoy my amateur drawings. It's quite fun at 12 o'clock at night. Oh dear, this is not off to a good start, is it? Okay, that's better. So yes, this is going to be an introduction to adversarial machine learning talk, and we're also going to talk a bit about some of the academic work that has been done in this area. So if you want to find me online, that's where you can find me. I rage quit Twitter about once a month, so I don't know how long that handle will be live, but yeah, my blog has my email address if you want to rant or send comments or anything like that. So before we get started, just as a little disclaimer, if you feel particularly inspired by any of the techniques here, please do not credit this presentation and follow the laws in whatever country you'll be inspired in. So why am I doing this talk? I don't actually work with machine learning day to day, but as someone who's part of the technology industry and who makes a living working with technology, I am quite concerned by the sometimes reckless application of machine learning to many of our daily problems without due consideration to the cost of these technologies and who is paying them. There is always a cost to implementing and releasing a technology into production, and the people who pay this cost are most often not the same people who profit from technology. And I think as engineers, that's definitely something that we need to consider. Right. So you don't need me to stand here and tell you that machine learning is probably the new magic sauce. It's in every startup, every product, even things that you wouldn't normally consider to be sort of a hotbed for AI now have some machine learning buzzword attached to them. So let's take a look at some examples. In 2017, you can get beer that has been brewed by a machine learning algorithm. You can also, if you are really bad at cooking or you don't own a watch, you can have a kitchen timer. Whoa. Sorry, the slides are cutting off. Is there any way to change the resolution?
One idea. I can kind of that, and I'll just drag. Oh, come on. How do you get out of full screen mode? Anybody know? Oh, 12. There we go. Should we present it not in full screen? That's really unhelpful.
I think that
okay, that's much better. That is much better. All right, so as I was saying, you can now get a kitchen timer that will help you cook your meals, and it's dubbed as the AI-powered home cooking sidekick. But the sort of weirdest and the most concerning of these is June, an oven that can talk to 192 CUDA cores. So when you put in a cupcake into June, she will actually run a machine learning algorithm to figure out that it's a cupcake, and then set the cooking presets based on what's best for a cupcake. And I actually wanted to check out if this is still on the market. It's sold out. So it turns out it's a pretty popular thing. Right. So I mean, it's all good laughs for us to be here and laugh at this, and like, okay, it's fine if June gets hacked and someone manipulates the machine learning algorithms there, and she thinks that the cupcake you put in is actually an oven roast and she burns it. Like that's probably okay. But increasingly, we're starting to trust more and more of the really important stuff in our society to some kind of software tool that's powered by a machine learning algorithm. Who here has heard of Equifax? Right. So you probably know that Equifax is not the best company to trust your data with. They published this report in February 2017 where they said that they were starting to use deep neural networks on the financial data they collect about people to help decide who gets a loan, who gets a credit card. I mean, these are pretty important decisions. Now, too bad that they couldn't use some of their MO expertise to try and secure their computer systems, because as we all know, a few months ago, it turned out that there have been gaping security holes in the Equifax infrastructure for God knows how long, and we don't even really know what data is going on into these models and who can manipulate them. Now, Equifax is not alone in using AI-powered algorithms to help decide who gets a loan or who gets financial assistance. There are thousands, well maybe not thousands, but at least tens of companies that are doing similar things. What's even more scary is this report from the Brookings Institute that not only welcomes but embraces the advent of machine learning powered software in the justice system to help judges decide who is more likely to commit a crime again when they are released from prison. I mean, now things are getting more serious, and you can clearly see that with this kind of software, the engineers who build it have an obligation to understand how these models and algorithms work when they are manipulated, or if they can be manipulated. And somewhat closer to home, we're starting to use a lot of machine learning, cybersecurity, buzzwordy type of software to secure various systems. And as you can see, this is a very lucrative field. This startup is about to go public with a valuation of $850 million. It's a lot of cash for machine learning algorithms that are not regulated, benchmarked, or verified by any certified body. Now, in the physical world, we of course have Google's AI driving cars, and this is a really cool piece of technology. And some of you might be wondering, okay, why should we even be concerned by this? Some recent benchmarks in image recognition and language recognition have placed machine learning algorithms on par with humans. So maybe we shouldn't be concerned about this kind of thing. But what if I told you that a self-driving car who sees a fancy stop sign that's decorated with some stickers would actually not stop, because it would classify this as go forward instead of stop? This is an actual example from a paper by Ivan Eftemov's research group, where they synthesized several adversarial examples that could be applied in the real world, and then they came up with these stickers that were placed on the stop signs and tested how well a state-of-the-art neural network that is trained to recognize road signs would fare on this, and it turns out not so well. So this has led to two prominent machine learning researchers, Ian Goodfellow and Nicholas Paperno, who are very well known for their work in adversarial machine learning, to say that in the sort of arc of this technology, we have reached a moment where machine learning works, but may be easily broken. So let's take a look at some ways that machine learning can be broken. If you've been reading the InfoSec literature, you're probably aware of the CIA model, which enumerates some features of systems and then categorizes them into the 3 different ways that they can be broken. So what does it mean for a machine learning model to have confidentiality? Well, this means that any model that you put into production will make sure that no one who is not authorized to view the training data will have access to it. So any machine learning model that you put into production will not leak any data to users who should not be able to see this data. And this is especially important for cases where you apply machine learning to healthcare. You wouldn't want someone being able to reverse engineer private medical records just by viewing the model. Now, this all sounds very nebulous, but as we'll see going down, it's actually quite easy to start probing the internals of these models, even if they're so-called black boxes. So the second part in the CIA triad is integrity, and this is where most of the academic research in machine learning hacking has focused on. So to compromise the integrity of the model means that you manipulate either the training data or the input examples in such a way that you severely compromise the model's accuracy, or you force it to misclassify obvious examples, such as the example with the stop sign. It's clear to us that that should be classified as a stop sign, but the neural network actually thinks that it's a sign saying drive forward. The last but not least in this triad is availability, and this just basically means that the machine learning system or anything powered by it works as it's supposed to. So for a self-driving car, compromising availability would mean putting some kind of marks on the road, for example, that would prevent it from driving. And if you've been around Twitter, you've probably seen this tweet that went viral a few months ago. This is the work of a British artist called James Birtle. He drew a salt circle on a road and then drove a self-driving car into it. And this actually traps the car, because for a car, that salt circle represents some kind of road sign that it's not supposed to cross. So this was actually quite cool and scary. Okay, but let's get started talking about how to compromise the integrity of machine learning algorithms, which is where most of the research has centered. So you've probably seen this famous picture. This is an output of the deep neural network GoogleNet that's trained on the ImageNet dataset. So the first picture is clearly a picture of a panda, and GoogleNet is able to classify this as a panda. Then we add a little bit of perturbation to it, and all of a sudden the neural network says, oh, this is not a panda, this is actually a gibbon. So this is what we call optical illusions for algorithms. This example was published in a paper by Goodfellow's research group from Google called Explaining and Harnessing Adversarial Examples. And there are two key lessons that were learned from this paper. And the first one I think is quite striking. It says the two images that are close in perceptual distance, so appear very identical to our eyes, may actually not be very close in the feature space of the model. So this sort of debunked a lot of the sentiments in computer vision research, which said that two images that appear close also must be somehow close in the Euclidean space. And the second myth that Goodfellow's group debunked here was that the reason why deep neural networks are so vulnerable to adversarial examples is due to their highly nonlinear nature. And they showed that this is actually not true. In fact, they showed that most linear models would be just as susceptible to adversarial examples, and this approach suggested a quick systematic way of generating adversarial examples. So if we think about a linear model, and we have a non-malicious example x, we can simply add a perturbation vector eta, which is composed of some values that we'll determine later, and we will get an example x star. So now when we pass this example through, when we take the dot product of this example and our weight vector to pass into our activation function, we'll see that the activation function will actually grow by the dot product of w, the weight vector, and eta, the little perturbation. So it's not totally inconceivable that by adding this little perturbation, we can actually push an example over a decision boundary into another class, which is what is happening with the example of the panda and the gibbon. So Goodfellow's group came up with this algorithm called the fast gradient sign method, which simply takes an existing example in the input space of the model and then perturbs it by creating this perturbation vector eta, which is simply created by taking the sign function of the weight vector. And they've actually made a Python implementation of this and released it in the Clever Hans library. So this literally allows you to create adversarial examples based on the fast gradient sign method with a few simple lines of Python code. So I do highly recommend that you check this out. Now, although this is all the rage in deep neural network research, Goodfellow's group was not the first one to come up with ways to compromise the integrity of machine learning. In fact, in 2013, Battista Biggio's group published this paper on poisoning support vector machines. This paper assumes quite a strong adversary. It assumes that A, not only do you know what model is being used, it also assumes that you have access to the training data and you are able to retrain the classifier, add some more data, and then retrain it again until you find a data point that maximally compromises the classifier's ability to classify examples. So, I mean, this is probably not something that you'll be able to pull off in real life, but anyway, it's a useful example because it presents one of the first instances where we were able to come up with a systematic algorithm to find adversarial data points instead of just blindly trying. So the first step, if you want to do this, is you define some kind of cost function that takes your validation data or input or training data and then measures the sort of classification, the overall classification error on that data set. Once you have this function, what you do is you have, in a two-class case, you have a class that's being attacked and the attacking class. So you pick a point in the class that's being attacked, you clone it, and you flip its label to be the opposite, the label of the opposite class. Then you retrain the SVM using some kind of optimal training algorithm, which means you don't have to retrain on the whole data set every time, or you could if you have the computational capacity. And then you recompute you recompute the gradient of your cost function, which you defined previously, so that you know which direction your data point needs to move in such a way as to maximize the cost function, so to maximize the damage that you've done to your algorithm. And then you basically repeat this as long as you want. So you can say, okay, I don't want my attack points to be too far from the original data set because that might cause people to be suspicious. Or you might just say, okay, once the change in cost function is less than some value epsilon, then I'll stop. So what you get out is this kind of picture. So this is the color gradient here represents the value of the cost function, so in our case hinge loss, as a function of the location of the attack point. And the little black trail that you see over there is how your attack point evolves over successful iterations of the algorithm. So you start over there. So that point is your first point. So you pick that randomly. It's not supposed to be too close to the decision boundary, but you may sort of have some leeway in how you choose it. And then you successfully iterate until you reach some kind of local maximum, the red area over there. So you might say, okay, this is all great for getting publications and citations, but like who really leaves their model parameters exposed? And like most certainly most people who make up data science APIs would probably also now like just let their training data lie around. So does this mean that all of our algorithms are secure? Because it's just too hard, you know, to figure all these things out. And by the time you start like forcing an algorithm to retrain, certainly some sysadmin or some monitoring system will have kicked you out. So for a while you might be calmed by this thought, but actually there is a thing called a black box attack on a machine learning model, where you as an adversary know pretty much nothing about the internals of the algorithm, the training data. All you know is its purpose. So for example, this algorithm is used to classify images, and you are able to query the algorithm on some examples that you send it. So this would actually be how you hack a data API that's hosted in a cloud, a classification API. So this was published again by Nicholas Paperno and Ian Goodfellow's group, and it's called Practical Black Box Attacks Against Machine Learning Algorithms. So in this paper, the adversary knows nothing except what the model does. So what the adversary does in this case is he says, okay, the cloud-based machine learning model is our oracle. It allows us to send it examples for classification, just as we would do, for example, with one of Google's or Amazon's cloud-hosted pre-trained solutions. And then we get to observe what labels the model sends back. So what we do is we say, okay, we're going to train a local proxy model, and we're going to send it some synthetic examples. We're going to send the oracle some synthetic examples, see what labels the oracle assigns to them, and then we're going to use that labeled training data set to train our local proxy model to simulate the oracle. Right, and then we're going to apply the fast gradient sign method or another method of your choice on the local proxy model to create adversarial examples, and then we're going to see how the cloud-hosted oracle actually does on these adversarial examples. So here is an image of two very famous data sets in machine learning. So the first part there is the MNIST handwritten digits data set, and the top row is the non-adversarial examples, and then the bottom row represents the adversarial examples that have been generated against a local proxy model trained on the synthetic data we received, the synthetic data and the labels we received from the Oracle. So, I mean, you can visually see that something's a bit wrong with those handwritten images. So the authors of this paper tested these classifiers against a cloud-based API that was called MetaMind. It was a bit later acquired by Salesforce, and they found out that even without knowing anything about MetaMind's internals, they were able to force it to misclassify 84% of the examples. Right, so in conclusion, there are several ways that you can compromise the integrity of machine learning models. You can poison the training data, but this is quite expensive and assumes that you have a lot of access into the system. You can craft adversarial examples by knowing some properties of the system. And if you don't know anything, like which is probably the most realistic example, you can train a local proxy model that actually fairly well approximates the functionality of the model that you're attacking. So what about defense? So shout out to all of my Peter Jackson fans. This is a screenshot from the Two Towers. So if you watch the film, you know that in this film, sort of the Kingdom of Rohan is trying to defend this impenetrable fortress, and they say, okay, we're all safe here except for this one little weakness that's in the wall that then allows the enemy to reach the fortress. So I guess it's a bit the same with machine learning, is that anyone who's defending a system has to build a perfect defense that will cover absolutely every single adversarial example that you can possibly imagine, which is quite an impossible task, whereas someone who's trying to hack a machine learning system only needs to find that one opening in the defenses, and then that's it. So there's an inherent asymmetry in trying to defend these systems. So does that mean that there is no hope? Well, Ian Goodfellow has been publishing some research papers on using adversarial learning to bulletproof some of the models that can be vulnerable to adversarial examples. And what you do in this case, it's sort of a brute force approach. So you say, okay, this is an adversarial image of Grumpy Cat, and you feed it into the model and say that's an onion, and you're like, no, that's actually a cat. So you sort of feed the adversarial examples along with the normal examples, and then you sort of help the model understand that these should be classified as cats as well. But other than that, we really don't have any bulletproof or good defenses at this point. How am I doing on time? So I have a few minutes left, but that's sort of all I wanted to cover, and I hope that even if I failed to deliver my live demo, I hope I gave you something to think about when you go to work on Monday, and sort of if you're building these systems, then you should think about how they impact the people who are using them, maybe in ways that we really don't intend. So I've left some resources at the end, and you can find the slides online, or you can just at me on Twitter and I can point you to these. But yeah, I'll be happy to take any questions or comments or criticism. Thank you.
Thank you. We have time for one or two questions before the coffee break.
What was your live demo going to be, just out of curiosity?
I was going to try to use the Clever Hans library to synthesize some adversarial examples and then just show you how a neural network can be fooled into thinking that a panda is a gibbon or a cat is an onion or something like that. If you just search for Ian Goodfellow's papers, he has an actual YouTube video where he prints out adversarial examples on just plain paper and then uses a iPhone-based machine learning app to try and recognize what that is. And it turns out that you can fool even these kinds of camera systems just by printing out adversarial examples, which is kind of scary.
One more question?
I was about to ask whether the adversarial examples had any indicators in them, like lower signal-to-noise ratios, that you could use to flag them as suspicious. But I think that camera answer just indicates no.
I'm not the expert on this, but I can certainly say that adversarial examples are not really detectable in any conventional means. And they're also quite transferable. So an example that damages one model can actually damage multiple different kinds of models, which is quite surprising. But I don't know of any way to sort of determine if something is an adversarial example.
One last question.
I'm not clear on how the model itself is damaged by misclassification. If I send an image and it comes back as something, I know that's not what it's come back as. How is that damaging the model on the other end?
So you're right. In that case, it's not damaging the model itself because we can't affect the training data or we can't retrain it. But I think it's damaging the model's ability to do what it's supposed to do in a way that we want it to do. So you're right. It actually doesn't, harm the model, but it would certainly harm a self-driving car using that model.
Thank you. Will you be around the rest of the day?
Unfortunately, I have to catch a train to London, but if you want to speak to me right now, then I'll be happy to talk.
Please thank Camilla again.